Let's try that same four-step process with a different problem where we're going to see something slightly different happen in our work along the way. So the very first thing I'm supposed to do when I'm trying to take some nasty fraction and break it apart with partial fraction decomposition is see if it's improper. So let's see, the degree on top is 2, degree on bottom is 3, so I don't need to worry about that. Okay, so step 1 is already done. Step 2, I'm supposed to factor the bottom. So let's go ahead and factor the bottom here. I'm going to leave the top alone. But for the bottom, I can factor out an x. And in fact, I could factor this even better. X squared plus 2x plus 1, that's just x plus 1 times x plus 1. Okay, so the bottom we could definitely factor out. Notice something new that's happening here. I have a factor that's showing up twice. Remember, in our steps we learned, we have to handle that a little bit differently. So upcoming in step 3, because we have a factor that showed up twice, we're going to need some number over the factor, and also some number over that factor squared. So let's see what that ends up looking like here. This is supposed to be equal to, so let's do the first factor, x. I'll just call it a over x. The next factor is x plus 1, so I'll call it b over x plus 1. And then, because this factor shows up twice, I need another term that's some number over x plus 1 squared. Okay? So now, let's go ahead and ignore the integral for just a second and see what happens with these fractions when I combine them. So if I add up all these fractions together, I would have a times, so a over x times x plus 1 squared over x plus 1 squared. I would have b over x plus 1 times x plus 1 x over x plus 1 x. And I would have c over x plus 1 squared times x over x. Just getting that common denominator of x times x plus 1 squared. So let's see, this would be a times x squared plus 2x plus 1, b times x squared plus x, and c x. Okay, so I can clean this up a little bit more. Let's gather all my terms together. So let's start by looking at all the x squared terms. I've got ax squared plus bx squared. Then I'll gather together all my x terms, so 2ax, bx, and cx, and then I'll gather together all my constant terms, a. And remember, all of this was supposed to be equal to that original fraction, 5x squared plus 20x plus 6. Over x times x plus 1 squared. Well, now that I've combined things, I can go ahead and make a system of equations. So let's start with the x squared terms. If I look on the right, my x squared terms are a plus b, right? That's the coefficient of x squared. So a plus b is equal to, well, if I look on the left, I see the x squared term is 5. So apparently a plus b equals 5. Okay, now let's look at the x terms. So on the right side, my coefficient of x is 2a plus b. On the left side, my coefficient of x is 20. Finally, let's look at the constant terms. On the right side, my constant term is a. On the left side, my constant term is 6. So I've got, oh, I left something out. There's a cx there. That would have been bad. There we go. All right, so this one's actually not too bad to solve. One of these equations is already solved for us, a equals 6. If I plug that into the top equation, 6 plus b equals 5, that means b equals -1. So now I have a and b. Let's plug it in here. 2 times 6 plus -1 plus c equals 20. So let's see, 11 plus c equals 20. That means c equals 9. So at this point, I've found a, b, and c, which means I'm ready to rearrange my equation using this guy that I found. Okay, so let's grab this and move it a little further down the screen. Just so we can see what we're doing here. Okay, now that we know a, b, and c, let's fill those guys in. Alright, so this is going to become the integral of 6 over x plus negative 1 over x plus 1 plus 9 over x plus 1 squared. Now, each of these little integrals should actually be pretty straightforward to do. So let's start with the integral of 6 over x. I could write this as 6 times the integral of 1 over x. I'm going to write this as 1 over x plus 1. And I'm going to write this as 9 times x plus 1 to the negative 2. So let's see, this first one, the integral of 1 over x is natural log of the absolute value of x. The integral of 1 over x plus 1 is natural log of the absolute value of x plus 1. Right? It's just that u prime over u pattern. This one is just going to be a power rule. Okay, so let's do a little bit of u substitution here. If u equals x plus 1, then du equals dx. Okay, so this is 9 times the integral of u to the negative 2 du. So according to the power rule, I should just bump up the power by 1 and divide by that new power. Okay, so I'm getting close to my answer here. Now let's simplify this a little bit. First things first, I'm going to use some properties of logarithms to combine these guys on the left. So I'm going to first write this as natural log of absolute value of x to the 6th. And then I'm going to go ahead and rewrite this in terms of x. So this is minus 9 over x plus 1. Okay, and one last thing I can do to simplify this, I can combine these logarithms using the quotient property. So I'm going to write this as natural log of absolute value of x squared over x plus 1 minus 9 over x plus 1, and then I've just got my plus c on the end. Okay, so let's recap what happened here. All the way at the beginning, I decided to go through my 3-step process, because I didn't have any quadratic factors, trying to factor this guy. Okay, I got it factored. And then I wanted to figure out a, b, and c that would make this work. Notice I had to have a c over x plus 1 squared term here, because that x plus 1 showed up twice. If it had shown up 3 times, I would have needed a d over x plus 1 cubed. Right? Just do as many terms as there are instances of that factor. Okay, I combined everything by getting a common denominator. I made a system of equations based on the x squared terms, the x terms, and the constants. That got me a, b, and c. And by plugging that into my integral, I was able to do each of those little integrals more easily, and I got to the answer at the end.